Good morning, everyone. My name is Knezevich. I'm an assistant professor at the University of Knezevich and I'll be the moderator for this session. Starting off, we'll have a quick introduction by the session sponsor, Michael from Stantec.
Go, Mike!
Good morning. It's not just me, you get a few of us, but just wanted to say good morning. Thank everybody for coming. This is a great Smart Summit. Had a great time yesterday and learned a few things and networking to top off. Just real quick, I'm with Stantec based on our Atlanta office. As you can see, we're a global firm, but we're very well represented within the Southeast and particularly within Georgia and Tennessee and neighboring states. We are very active in ITS Georgia, ITS Tennessee, and we're very involved and happy to have been on the planning committee and sponsorship committee for this summit. So, we are a full-service ITS firm. We take projects from planning, concept level to design integration, and we're happy to thank you for the opportunity we've had to work with many of the clients here in this room. And with that, I want to hear from a couple of other members of our team, Esteban and GDOT.
Thank you, Mike. Hello, Zach. I'm with Stantec, and so we've been working with GDOT for several years on many ITS track projects. We recently supported TDOT in developing their ITS and fiber deployment plan, which I will present about here in a minute. The effort led to the identification of a project that was a good fit for a SMART grant that we supported TDOT in applying for and winning related to truck parking availability systems with in-vehicle messaging. So here's their video.
Derek Gudu, I'm electrical engineer with Stantec, and I work out of the Atlanta office. Project I'm particularly proud of is Louisiana, and this is showing that it recently completed construction in, I think about June last year. And so it's an area between Baton Rouge and New Orleans, about 20 miles south of I-10. And we didn't have any ITS in that region, and it's a blind spot for service control, as well as a pretty important hurricane evacuation route. So because it's a pretty swampy area, you can see the rural natures from that site. It was very difficult to get power to these campsites, and to have continuous camera coverage, had to get a little creative. Power company gave us some estimates of roughly a couple $100,000 per site to get power brought to these cameras. So that was obviously not going to work. We came up with a very robust solar panel and battery arrangement to try as part of the typical installation. So the little graph, that's kind of an eye chart, but it's basically showing that during the hurricane they experienced last fall, the site did not lose power. It remained power for the entire period. So, thank you.
Thank you, gentlemen. And with that, let me introduce our presenters for the first session. Please help me welcome Jack Domingo from Stantec and Andy Barlow from Tennessee DOT.
Good morning, everybody. Sorry, trying to figure out how this thing works here. So I had to be here today talking about a little bit what we have in our So talking a little bit about what we've done recently with TDOT on our ITS fiber deployment plan. So talk a little bit about what we've done here. So we embarked on this effort. I got TDOT, I guess, about a year efforts that was presented was talking through what we needed to do with our ITS deployment plan. So part of that, we realized the needs there. So there was a lot of different needs. Part of it was going through trying to identify what we had from an asset standpoint. So that kind of gets a little bit of the topic today, what we have with the asset management aspect of it. And so when you get into the asset management piece, give a little bit of my background. Before coming to TDOT, I went to the city where we had utilities. And so when you have that, you really need to know what you have, where you have it, and trying to map that out. So one of the big things, so why of this really kind of gets into the purpose of you have these assets that are in the ground, they're overhead, they have a life cycle to them. So how do you take care of that? How do you own that? How do you maintain that? And so one of the big tools that I look at myself is GIS, and using that for mapping purposes. You can do so much with that. I love it. And we'll talk a little bit more about that later. One of the things that I really love is just being able to spatially locate everything, see where everything's at. You know, in proximity to one another. You can filter via GIS and attributes the whole bit. So that's one of those tools that I just really appreciated from my time there. And then we had that opportunity to go through that as we get into this process. So you see the wheel here, talking about the deployment planning process, what we have for TSMO, which is not traffic, it's transportation systems. So we talk about that all over this, folks. What we talk about today is more on the ITS side of things, which ITS is an integral piece. So you've got our wheel here, so we start at the top, you go through deployment planning and what that looks like, and we're following around, kind of around to the right, going through analysis, construction, then you got to get down to maintaining your assets. So really kind of the LPs down below is what we want to look at. So that's kind of what we're at. Of course, see how that will feed back into performing, measuring, seeing what you need, and it fits back into the project, getting into the project process. So why GIS? I mean, I talked a little bit about visualization of things. You can go in, you can be interactive. You can make it as simple or as robust as you want to make it. It's very scalable. And so you can go in there, look at that. This is a screenshot here of what Stantec put together for us, our plan. We have inventory, 788 fiber pull boxes. There's all the kinds of conduit, everything like that to keep track of. So you also want to do with the tracking long-term projects, add projects in there, you can manage the construction, well, at least the elements of that, things come online, so you can add tracking from that. So the other part to it, I think, and this will get on here, kind of get to the deployment and methodology.
So yeah, I think the beginning of the process was a lot of coordination with TDOT and the different regions. We needed to get everything that they had existing out in the field first. That's what we wanted to gather, see where any gaps were. So then once we got all the KMC information and information from Smart OCS, we held some stakeholder meetings and got with different entities, municipalities around the state, THP, to get their input and their insight on where they find most issues day to day. And then they did identify their most troublesome spots. That led us to some project identification. And within that project identification, we were able to kind of rank them with a system I'll go over later to then prioritize the projects in order to basically have, a certain amount of funds become available. We have a list of projects that are necessary at the top of the list that everybody in the state basically agrees with. And then that'll lead to a roadmap on a process for TDOT to get all these projects going. So for the data collection effort, we got KMZ files from TDOT from every region, and we blended them all together into a map, and then also we back-checked everything with what is live and available in Smart CS that you see on the side of the road, because there's been a lot of maintenance and updates and upgrading. As you can see, Matt's got a video here kind of showing the ease and the simplicity of the GIS database with the checkboxes, with the different layers. It's got existing devices, projects that are in design and construction, newly planned projects that we heard from the regions of where they need infrastructure. So all that is pretty simple and simplified within the GIS database. And then we were going to bring in other layers that are public from TDOT, as in the mileposts, rural help routes, and various other layers that are useful in looking at potential projects. We also did a bottleneck and safety analysis with help from Marge, and that helped visualize troublesome areas, and you can put the safety analysis layer on with the existing devices, and you can find where you might have gaps in troublesome areas, all very simply, very easily. I'd like to get things moving around that one. So for the stakeholder engagement, yeah, those are some, there's a list of some important stakeholders that we had together, and it was just a long week of talking about, stories and nightmare situations that they dealt with in the past that they still don't have any ITS or technology infrastructure out there. So stakeholder engagement at the beginning of the project was, in my opinion, the most important, because we heard from everyone. If anybody was in those meetings, you know how productive they were. So project identification came from those stakeholders. There's a lot of fiber in the state. It's mainly centered around the metropolitan areas, but that's not the only place you have issues. So we got together and really went over every nightmare story that I could think of came from stakeholder meetings, and really were able to identify some projects. We were able to do some large overview cost estimates to kind of get that information from TDOT to say, okay, well, here's what it would look like when we're going to build this trouble spot with some ITS to help with the traffic incident management. And then here's the criteria that we prioritize projects with. Everything was given a ranking that went back and forth with TDOT and stakeholders to where it's a very collaborative process. And we were able to give each project a score, essentially, based off of these criteria, and rank them by a stakeholder. And then this will lead to just a plan, a roadmap for TDOT to use in the future to get some of these ITS projects going and out of the quarter.
Thanks, Zach. As we kind of went through the process, that's pretty much finished now with the deployment plan and this. So the things to talk about, we talk about with the GIS consideration. So I think one of the things that you see Rue up here. So you acquire the data, then you process it, and then you've got all kinds of issues. So I think one of the things we realized is we have a lot of data. We're very data rich. So then what do we do with it from that point? How do you use it to best come up and meet the objectives that you need? In a lot of ways, I think we're still, as an industry, I think we're in a lot of ways finding the data that's just coming up, new data every day, trying to gather it, process it. Our motion project we've run through, there's all that you want to know. So then how do you apply the possibilities are endless? Sometimes that can help not utilizing that through GIS, and look and see, okay, what's our model? Let's focus in on what the problems are. Let's focus on the data that we have. Let's see how we can integrate the data to match up with the solve that we have. And I love the geospatial ways to be able to do that through GIS. So, schema is a little bit of a screenshot of some of the schema that we use for this one. And, you know, a lot of this, and I know we had some talks internally with TDOT, data governance. Basically what all that stuff means is make sure that your attributes and elements, you got them coded right, they're in the right place. You know, if we have US 70, SR 24, you put a dash, you put a space, those kinds of things. You got to make sure, otherwise you have to look at a bunch of different ways and different places. So next step, you know, obviously we've got a deployment plan that's going to feed in the project process. We get that going. But the big thing for, I think, what we have is present now. This is courtesy of Matt, I think, trying to find a pool house down in Alabama, I think is what he said. So, you know, it was a pool house that had been built over on top 30, right? 60, where is it? So, you know, trying to figure out where some of it is at. So, you know, this is getting into several different ways. Just knowing what you have and where it's at. Get into project planning, surveying, things like that. So you can tell. But then the other side of it, just from the maintenance aspect, maintenance contractors across the state, how do you process that? How do they fit into it? What's that interaction look like? It's ticketing software portion of this going to look like. So those are all next step, next level kind of things to keep in consideration. So this is the bar chart here with some lines and numbers on it. Basically, just think about this as sort of a financial model. Using what you have, projects that you have, you can continually be updating costs of these are all $24 numbers, so you can escalate that based on inflation. But to give you, you have projects that you can lead, which is you have what you have. It's a little bit of an involved process, but let's consider that fixed. You have that, you have say costs associated with that, or your variables funding, and so then you can take that and try to make this chart go out 12 years here, go out 5. So in reality, it's probably go out longer. So that kind of helps you give a tool so you can utilize the tools that you have, the deployment plan, GIS, putting those together into a financial model. This is just a screenshot here of what we have statewide, and try our best to confirm these numbers. Like I say, there's a huge effort if you wanted to go out and geolocate everything. We're not quite there with all that stuff yet. And that's one of the next steps that we want to try to pursue. In some ways, we just have to get a shot if we get behind the cover and try to find out where stuff's at. So, I mean, it can give you an idea of what it really look like with certain systems. Obviously, there's a lot more to develop. So, any thoughts, questions? Appreciate it.
Thank you, Zach. Thank you, Andy. And now for the second presentation of this session, titled Next Generation Firewalls for Traffic Signal System Security. We have 4 presenters. Josh Montgomery is a seasoned automation engineer with experience driving innovation. Sam Brown is the critical infrastructure sales lead for Palo Alto Networks, where he spends time educating customers on security solutions for critical infrastructure applications, including transportation, public works, utilities, and aviation. Previously, Sam served as the Director of IT for the Georgia World Congress Center Authority, managing infrastructure and systems for the Georgia World Congress Center, the Georgia DOT, Centennial Olympic Park, and the Savannah International Trade and Convention Center. Steve Asborn is an accomplished network engineer with extensive expertise in designing and implementing advanced network solutions. His work has been instrumental in optimizing and securing the department's ITS network over the last 15 years, ensuring reliable connectivity and robust infrastructure to support critical operations. Please help me welcome the presenters for the second presentation.
Stretches across thousands of roadside cabins throughout the state. We have significant security concerns security concerns. Specifically, we worry about it all runs and vision being access to these cabins and intentionally connecting to the network. While there are efforts to improve upon physical security, we need to do what we can from the network side to limit the scope or limit the impact of such a breach. Before this effort, we lack visibility and habit of traffic leaving these cabins, whether it be going to a traffic device in the net or to a resource at a GDOT office. In addition, we have a lot of third-party contractors that have access to these cabins, and in a lot of cases, they don't use GDOT to manage laptops, and therefore they may or may not be updated or patched related to vulnerabilities. In addition, we have a lot of traffic devices in these cabins. That in a lot of cases weren't necessarily designed with security in mind and might be running against security links. And then finally, the current cabinet networks, while they have a level of fault tolerance built in, there are failure scenarios that the current design is not working out and can result in that being offline. So with that, we set out to find a solution that would introduce a security boundary at these cabins and give us that visibility on traffic leaving the cabin, as well as be able to enable us to inspect traffic at the application layer, and also enable us to allow only the necessary traffic flows. We also worked a solution that would let us discover and inventory all the connected traffic devices and be able to ensure that they're not a threat to the rest of the network. And then also we want to add rate routing capabilities to these cabins, so as to maximize uptime and minimize the impact of various outbreaks and outage scenarios. And then given the scale that we're working with, it's imperative to have a streamlined deployment configuration process, so as to maximize efficiency of GDOT resources as well as field techs at physical cabins. And so after reviewing offerings from our area partners, we decided that the best fit for us was the security solution offered by Palo Networks, as it met all of our requirements, as well as integrated with GDOT's other security initiatives. So here to talk more about that solution is Palo Networks.
Thanks, Steve. So to replace or upgrade the cabinets in the field, GDOT opted for our PA 450 or 5G firewall. It offers both fiber connectivity and 5G connectivity. GDOT opted for several services running on this firewall, our advanced threat prevention, which is going to inspect all of the network traffic leaving the cabinet destined for the data center, as well as IoT security, which is going to provide visibility and enforcement, and SD-WAN for its advanced routing capabilities, and also assists with the automated configuration and deployment of these firewalls, which Josh will touch on momentarily. To give you an idea of how this works, in the middle here you have what would be a typical traffic cabinet. You might have a router in there today. You might just have an Ethernet switch in there today of some sort. Once you put the firewall in the cabinet and start connecting devices, the firewall is going to first start sending telemetry data to our IoT security cloud, which is going to provide an inventory of connected devices. It's going to provide
vulnerabilities associated with those devices, assign a risk profile to those devices, and help the engineers understand what normal device behavior is. Up at the top, you see the camera there, that's called an access camera, right? We expect to see streaming video from that camera, RTSD. We expect to see DNS, DHCP network protocols, maybe FTP, some sort of FTP service where it can get its updates. Once you understand that normal device behavior, our IT security cloud is going to start recommending policies to adopt on the firewall that says this camera can only send these applications across the network. And if that camera starts acting like anything other than a camera, if all of a sudden you see a connection up to the Middle East from that camera, we're going to block it. Okay? So it gives you very granular control over what each of the devices in your cabinet can do across the network. Lastly, we're going to inspect all of that traffic over an encrypted tunnel. So all that data leaving the cabinet going up to the data center is going to be encrypted and inspected for any malicious threats. Overall, it really met GDOT's requirements for the next generation of their network. And Josh is going to come and talk briefly about the automation efforts that they put into deploying and upgrading their field cabinets.
Thanks, Tim. So, when we're talking scale, we're talking for GDOT, we need to automate. Right now, the engineering team for the network side is 2 people. We're not going to deploy several thousand firewalls with 2 people at full time, scheduled 50 a week. It's just not going to happen. So we took the approach of we need to automate the deployments here. We need to provide self-service for the field techs so that they can deploy in the mornings, at night, whenever they need to deploy, depending on any issues going around, fiber cuts, things of that nature. And that way we don't have to staff IT. If something happens, of course, they'll reach out to us or we get automated or the deployment failed. So that's a big piece of what we want to do. A couple of the other things we'll talk about here is inventory management and kind of the platform expansion. So first we'll kind of hit on field deployments. Everything that we're doing with the field deployments is built in-house, utilizing open source tooling. So we took the approach, like I said, of we want to empower the field techs with self-service. We don't want them to wait on us for staffing and other things. So they go to the web page, they put it in the site that they're at, they put in the serial number of the firewall, they press go, they walk away. The system will deploy the firewall with pre-checks, post-checks, and provide visualizations of where it's at in the process and if anything's failed. If there's a failure in the process, the IT team will get notified that there was a failure, and we work with techs to go back out to the site and troubleshoot the issue. We'll expand upon troubleshooting through self-service tools, but as an MVP, first go at it. There's certain things that we want to do and get out there and enhance the text as fast as possible as we are scaling up performance. The important part to me is providing that empowerment of text, especially with what is up and what is down when they get to the site. So self-service provides the pre-check. It has inventory of everything at the site. It runs a health check on all the devices, so the tech goes, hey, this was up, this was down before they even got there. Once it finishes, it runs a post-check, and it says, hey, this is now down, you may need to check this, we need to troubleshoot this. So it provides that safety net of knowing what was on, what was off, before and after they got there. Some of the ways that we power this is through the inventory management. I'm sure a lot of people use Excel spreadsheets. They're great, but they're not good for automation. So what we have done is utilize an open source tool called NetBox, where it's providing the network inventory management. We have all our IP allocations and all the network allocations in it. We also have site allocations where it has information of the devices at that site, and it has an API that can provide the scripting or reporting or anything you want to do. It's very extensible, but it provides network models in an easy way to access or anything that needs to look at it, and it provides us a platform to automate on top. I kind of finally want to talk about what's next. So right now we're focused
sitting there and doing it manually, or you have automation. You already have the pre-checks, you have the post-checks. Building the automation to do the deployment itself, the upgrade itself, is pre-triggered. So that way we can set, hey, every night 50 deploy, or 50 upgrades. Not a problem. We can do it on a set schedule, we can do AECOM came out, we need to deploy all 6,000, 8,000 tonight. It'll roll through it, no problem. We're confident that, hey, we have a pre-check, we have a post-check, everything's up, we're good to go. If anything happens, we can stop it immediately. One of the other pieces is expanding the visibility that we have in the network. So with our MLS network, we can stream telemetry off all the boxes. We're looking at expanding that and partnering with Palo Alto to do that against all the Palo devices so that we're not taxing CPU with SNMP all the way at 5 minutes, 10 minutes, or whatever you can do. We're streaming it at 5 seconds, 10 seconds, so we're getting more granular data and providing a better visual of what's going on and a more accurate visual of what's going on. So that's including kind of the automation at a high level. I'm going to hand it over to Esteban, and he's going to talk about the actual deployments.
Thanks, Josh. Yeah, so Josh just kind of spoke about the deployments in the network as a whole. So I'm going to very quickly go over into the field installation part of the deployments, and then kind of how we went about this in Georgia. So far, GDOT has upgraded to these new Gen firewalls at about 80 locations so far, statewide. So from the North Georgia to Southwest Georgia, near Savannah. We have developed a process that works with the majority of this existing infrastructure that GDOT has right now, which is like their 332, 336, 337 cabinets. And then as we are doing these deployments, we want to standardize as much as we can for ease of installation and for future troubleshooting. So one of the goals that we have is that we wanted to have a consistent and tidy installation. So basically, we wanted to avoid scenarios kind of like you see in the picture here, where the router or the switch is at the bottom of the cabinet with a bunch of wires around it. We wanted to have a tidy installation so that it's consistent for techs to go in there and know exactly what they want to see and troubleshoot it and go in and out because they can't go on their next task. So some of the early challenges that we had or that we faced was the sheer size of this new firewall. So here on this next slide, you see kind of the size of it in comparison to the cabinet. This is a GDOT standard 336 cabinet. It's one of the smaller compact cabinets. You use a lot in downtown area type scenarios. So we designed the shelves and the mounting and the cabling kind of ourselves in order to fit in the power unit in order to fit the scenario of the cabinets. Typically, this is one of the hardest cabinets that we would have to face. So we put a lot of thought and engineering to kind of the best solution for GDOT for ease of use. And this is typically an installation that we found that would work for a 332 cabinet with a shell down on the top of the cabinet itself. And another area that we wanted to focus our attention in is standardizing with port assignments for a particular device. And as most of you guys probably know, and like I mentioned earlier, the technicians, they don't have a lot of time when they're in the field, so we want to make it as easy for them to go in and troubleshoot. So having this kind of port assignment standardization, it just helps saving time for everybody, the engineers in the office, the technicians in the field. So there's a lot that can mention about deployments, and there's more that we'll learn as we deploy each device. Because we're kind of working through these and network resiliency portion.
Thank you, Esteban. All right, so yes, as I mentioned earlier, while the cabinet networks had a level of fault tolerance, there are situations, in various areas that the current times don't work around. So if we look at this first slide here, the thing to notice here is the string of cabinets that are all operating in the model. And they're sitting between two hubs with routing, electric routing. They're all in the same subnet, and they rely on the GDOT hubs to advertise that subnet to the rest of the network. In this particular scenario, we were relying on protocol to dictate which of the two GDOT hubs is the active router at any particular time. And in this particular scenario, our hub E is the active router for that. And he's telling everybody on the network, hey, come to me to get to this subnet. So in this next slide, you can see, just for instance, assuming there's power outage at hub E or power break, you can see that our hub F, the hub on the other side, becomes the active router, and the cabinet network stays online, running free flow network. So where this current design has its limitation is if there's power break within that chain of cabinets. As you can see in the slide here, what's going to happen is both routers are going to try to advertise that network, that subnet, and the network's going to choose the best path. In this case, it chooses hub E. And so the first two cabinets remain online, but the other four cabinets, they're all online and reachable. So with adding routing capabilities to these cabinets, you can see that every cabinet is in its own subnet, and it's advertising its subnet to the rest of the network. And in this particular scenario, with this design routing protocol we're using, the routing works around this power break, and you can see one hub's advertising two of the cabinet networks, and another on the right there is advertising the other four cabinet networks. So everything's remained online. So what are the outcomes of this effort for GDOT? With next-gen firewall features that Palo Alto solution provides, we're able to create policies to restrict what the traffic devices can talk to the network, and as well as how other things. This includes restricted communication or data centers to only the necessary applications, as well as inspecting the traffic for the latest vulnerabilities and threats. We were also able to leverage the IoT feature to dynamically profile and discover these traffic devices and protect against abnormal behaviors. We have the ability to isolate the devices if a threat is detected. For our cellular connected cabinets, Palo Alto's SD-WAN feature enables dynamically form encrypted tunnels to both our data centers and routing protocols to route around those traffic breaks and access areas. And that concludes our presentation.
Thank you, Josh. Esteban and Steve. And now for our third presentation titled Evolution of Artificial Intelligence in Transportation, from ITS to Smart Systems. We have two presenters. Dick Adams is a PE in multiple states and a PTOE with a master's in transportation. He has over 35 years of experience in traffic and ITS engineering at state and local levels, as well as consultancy, manufacturers, and vendors. He started at WSDOT in signal operations in the city of Lymewood as the transportation engineer. Moving to the private sector, he worked for consultants, manufacturers, and vendors with 4 years as the ITS maintenance director for the GDOT. He has been the director of ITS transportation and control technologies now for over 6 years. Dick Adams is married for 31 years, is the father of 5 and has 3 grandchildren. Ben Adams is a technical support engineer for CD based in Atlanta and supports ITS in Tennessee. After learning and advancing in ITS from a major product in Hilton Head, he has gone on to work with consultants, contractors, and agencies on deploying and the support of new advanced ITS technologies. His support has recently focused throughout Georgia and Tennessee, specifically Nashville and Franklin, to install test sites. Please help me welcome Tim and Ed.
How's everyone doing? And I won't be wrapping this presentation today, so don't worry about that. So when we talk about AI and the increase within devices that we're putting out in our signal cabinets, with this, we're going to be, just for everyone on the base level, we're using AI very loosely. There's lots of forms, there's machine learning, there's automated general intelligence, there's just smart firmware, so we're just using real high-level, just intelligent firmwares all around. So as this continues to be more present within our industry, we're going to see it help traffic flow, we're going to see it help engineers, we're going to see it help consultants, and really at the end of the day, it's bring more safety and allow everyone to get to their startups and their work and everything safe. So as we go through, we're going to talk about radar detection systems. So this is integrating radar with cameras. You're able to use SDLC communications inside your controllers. Get 64 outputs. Obviously, with future ATC cabinets, more outputs will be presented in the future. But with this allows a web interface, which is really important for technicians or anyone going out in the field, right? You don't need a special kind of software, you don't need anything else, you can just get on a web browser and get inside the technology. So it's really good all around and allows you to do a lot of things. So with this, you get an aerial stitch photograph of the intersection, you get your targets, your cloud point data, whatever you want to call it, and you get eyes on it, right? So not only can you visualize these things remotely from your office, you can actually go and configure and put outputs right through your desk, right? You don't need to have technicians go out of line. Technicians can actually see problem, fix it, mainly remotely unless it's a power issue, right? You get your comm module, and with these technologies, the cool thing is the hardware is there, right? So you get your Gen 4 PLC chipsets, you get all the hardware, and the only thing you're changing is the software. So in this video, what you're seeing is a newer stitched technology that we're testing out in Florida. We're doing testing out in Hilton Head. If you have seen our presentations all last year, Hilton Head, we did a full upgrade. And so what this is really doing is this is taking a basic aerial stitch photograph, and radars are seeing one approach, and you're programming that, to now the radars are intelligent and can actually talk to each other and hand off that cloud point data to the next radar. So again, another form of intelligence within your system that you will be putting out there is that as things continue to progress, you're able to get not only the same hardware, and all of this is software on top of that, right? The next I guess, version of an intelligence system is thermal video, pedestrian vehicle detections, right? I know some agencies that are a little worried with TV cameras going out, and the public is scared for their security and personal things. That's all fine. Thermal's the way to go, right? So you don't actually see faces and license plates and things like that, but you can still get your benefits out of the technology. So not only can you get that technology at a lower price, but you can also get AI on top of that technology as well. So with that here, this is a base level. You can get your CCTV video of it. You also get a 100 resolution thermal image. Right, you can do the same thing like with radar. You can actually set your outputs, you do your pedestrian threshold, you can do a lot of things. Which the cool thing with these technologies, of course, I like to geek out and get down into the weeds on things, but a lot of agencies only use about 10% of the actual capabilities, right? And so as we move forward, you can see now again it's a web-based interface where you have everything right there, for your technicians, and you can do everything pretty much remotely, right? Also can seamlessly integrate with 100 resolution thermal cameras. You can also seamlessly integrate with 600 resolution in AI, right?
So adaptive control uses machine learning. And what that means for us is it's been around for a very long time. Some of the older people may know that the adaptive systems of the past grabbed a lot of data, shoved it to the central system, did processing at a central server, then sent the operations back out to the controllers to operate the signals. So a large pipe back and forth. The evolution that we have now is the adaptive system is more distributed. In this case, what we have is an adaptive firmware that resides on a controller, parallel with the actual signal firmware that runs the intersection. It interacts with the data that's collected on the signal firmware, and it does its processing. So it will do the calculations for cycles, and splits, and offsets, and it communicates on peer-to-peer networks. So the central system isn't really needed to run the adaptive, but it also helps to have a central system to kind of do all the signal operations that you can. So it uses the peer-to-peer network, and in addition, what it does is it will write to a pattern on the controller, and then the controller basically maintains operations. In the old legacy system, the controller became dumb terminal. So the idea here is that all your detailed programming in the controller still operates, and it's running then the new cycle, split, and offset based on the data that's collected on the higher resolution inputs. In addition, what we also have is the web browser interface to the adaptive system, both locally and for the entire corridor, so you can look at both local parameters and network parameters at the same time through a browser interface. So AI safety analytics is kind of a newer thing that has come onto the market. It is utilizing edge computing, so it's out there connected up to existing detection systems. So regardless of what you have, you can pull in that data, whether it's video, radar, whatever it could be. So the idea is that with that, it will do predictive analytics, and it will also allow for you to look at an interface, collect the data. All this is on the cloud right now. That is kind of where everything is residing for this particular technology. But you're able to look at near misses, you're able to look at vulnerable users, your data comes in. Any event that you configure in there will have a video clip that you can then go back and look at. So if you want to see wrong-way drivers, if you want to see where pedestrians may have been near missed by a vehicle, you can look at what was the cause of that. Did the pedestrian violate the walk, or was the vehicle violating a green? In addition, a lot of this data will be put out there so that you can look at trends. You can look at analysis before and after. Heat maps will give you the information so you can hone tune and find where you may need to do some solutions. And some of those solutions may be physical solutions. So it just helps you identify where potential problems may come up, especially on the near miss. So rather than traffic engineering being reactive to accident history, we can be more proactive to say, we've got a lot of near misses here, let's try to figure out how we can minimize that. And so that's kind of what this helps with all the predictive analytics. All right. So what we did was we put together sort of a table of some projects in sound here that we worked on over the last couple of years or currently working on, and just to kind of give a summary of what some of the technology is for these different projects. And as we go forward, we're hearing agencies want to add to it. For example, there's a future analytics that they want to put in because of their pedestrians and tourist corridor. So this just kind of gives you a brief summary. I'm going to go over a little bit of these projects and kind of give an overview of them, and then hand it back over to Ben to kind of wrap this up. So the first project, and some of you are aware of this, is the Hillhead project. So we wanted to thank the town, Jim, Darren, and Teresa for their help in doing this, and also Eamon and Eugene for the deployment of it. This was a very fast project. It was a 9-month project in which we upgraded 25 signal controllers. We put on the new firmware on AECOM. We also put on In addition, we put on almost 100 new radar units, one for every approach to the town. What that meant is we basically added a lot of detection for the town. And we have 2,200 or more detectors now, zones on the radar system that are feeding not only the operations of the traffic signal, but the adaptive system as well. With that, we've also put in 137 thermal detection for pedestrians, and we do density monitoring so that we can pull in a walk 2 times if we have a lot of pedestrians that are there. We also are working on the head canceling, so if the pedestrian leaves the area, we can then cancel that head call, so the driver gets frustrated that, hey, the walk's on and nobody's walking. Nobody's there. So these are things that we're working on. In addition, we use the central system. It was the Q3 Kinetics on cloud. We use the built-in TSMO reports to basically do a before and after analysis to see how well we were working. In Sarasota, Florida, we have a SA2 project. Tommy was one of the guys that ran out in the intersection to kind of show how this works, but basically we were focusing on head safety issues. And what we had there was basically not only passive head detection, but also how do we extend heads, how do we hold the head if there happens to be somebody just walking in the intersection and just sits down. So what are we going to do? So those are kind of the things that we did. This is a quick video of what we're doing. We basically had a walk time of 10 seconds, but when Tommy in this example just stands there in the middle of the crosswalk, it extends that walk up to 40 seconds. And so those are parameters that we put in the controller so that we can see how this would operate to help protect the pedestrian. So these are some of the AI technology that we're deploying to help increase what would be pedestrian safety in this particular project. You can see Tommy just lounging out there in the middle of the intersection, and the time is now when it's already almost at 20 seconds. We don't have to wait for the whole thing. Trust me, it was full. So, Charleston, and this is a shout out to Troy from the city, as well as a number of people from Q3, CT, DIRT. This was an NHWA grant that just came out, and so what this project is doing is it's addressing pedestrian bicycle safety on a corridor that's one of the highest ranked in South Carolina. So what we're going to do in there is we're going to basically deploy the AI technology, start collecting data. We're also then going to put in detection and change the operation, work on the operation to address some of the concerns that we're having for what we detect from the AI solution, and then move forward into what are the best solutions. So in preparation for this particular project, we upgraded to a cloud-based mobility ATMS system and getting it all online. So this is something that has just now started here this month, and we're moving forward to start implementing the detection and all the AI algorithms to start looking at what really is the issue going on in this corridor. And back over to
All right, I will just touch on Franklin, Tennessee, briefly. Franklin's really been pioneer. They're pushing a lot of technology, not just technology that we put out there, but technology just across the board, right? So they're working with radar, AI, LiDAR, and everything, just testing technology, right? So as far as CT goes, we have our MACTech firmware out there. We've been working on a central system with regard to mobility. They deployed about 11 locations, and they're continuing to make awesome upgrades. Shout out to Adam Moser for allowing us to come out there, and always great to work with him. Stanford Electric and Abby as well. Next one, we'll talk about Nashville. I love Nashville. I've been to Nashville, I came from Seattle over to the south, so it's fantastic. So they love thermal detection. They really like it. A lot of times they do it on fixed time, so putting out some detection out there is really awesome. It's great to work with a lot of the crew down there at the Signal Shop. They're really taking to new technology, and we all learn from each other a lot of things. They're also doing some cloud-based TSP operations with an awesome company Light, and they're really moving forward, as well as testing some radar off-ramp applications. Actually, we just installed like last week. So we're working on putting radar out there and being able to not only see and detect stop bar, but also put out some Q detectors about 600 feet out, and maybe run a flush point in case the off-ramp gets too busy. And of course, aside from what we do, they're also testing a lot of LiDAR, and Nashville is really being a pioneer moving forward, right? And so, of course, I geek out all the technology, but it's really awesome seeing agencies and cities and states actually moving forward at a very rapid pace, right? And the future is going to be really awesome for Nashville, so I'm super excited for that. Another project we're working on, I got to give special thanks to Thomas Lukert and a lot of people from the AECOM, Tommy as well. We're actually doing a safety pilot project out there. So a lot of vendors are coming in, they're testing different technologies. Where the main goal is just making students ride safely to school, right? So when they cross the crosswalk, they're coming in a huge group of 50, 75 kids, maybe even 10, but for the most part, big groups of kids, we want to make sure that they can all safely get across and want to just smooth the walk. So we're working on doing some ped extensions, walk-twos, kind of floated the idea of doing some other things. But again, it's really just putting technology out there and really pushing it to its limits, right? So no real rhyme or reason or what's going on. It's just saying, hey, let's just put a lot of technology out in this world, let's see what all it can do, and we're just going to fluidly, put it through its test, right? So that's awesome. Here's kind of a quick snapshot. I had some issues getting to the GDOT SIGOPS, but it's kind of AI technology, right? Where we're actually able to see, okay, is this pedestrian, is this bike, is this quote-unquote bike and pedestrian, because sometimes it's AI, bicycle, it'll detect the bicycle, and the person on top of the bicycle. So again, working with this technology is awesome. You can really do a lot of cool things with this stuff, but a lot of agencies, they just want to kind of bare bones, like just give us an output and let us do it in the controller, but really the technology is great. So here's another location we have on Ponce. I believe this is this Bullwater? Yeah, I don't know if this is Bullwater or Oakdale. I think it's Oakdale, yeah. So what this is going to do is this is our AI. Look at the top right. We're actually intent with this pedestrian. So again, we're testing another technology on really being able to give an output to the controller, do a predictive output, do an extension, again, whatever the agencies really want to do with this stuff, it's to just put it out there and say, hey, here it is, and how do we want to move forward? So again, that's another instance where we're just bringing this technology and it's forward. Next, I got to give an awesome shout out to Esteban Jones. It's always great working with him, right? He's out in the district. Cities man as well. But we're doing the same kind of thing with Nashville. We're pushing some of this radar technology. We're able to see 700 feet out. We're able to really get some distance. Just with one radar, right? So you can get your stop bar, you can get your advanced Q detections, and they've been able to really lower their delays without putting on some of those off-ramps. So obviously they're looking to deploy more of these, but hopefully they'll go all the way up and down the I-95 corridor and possibly IC. Geography, right, with Georgia. But again, thank you to all involved. It's great to use this technology. That's the fun part. Every technology isn't made for every scenario, but what you really know your technology and know what it can and truthfully what it can't do is going to be really beneficial moving forward. So, thank you.
Thank you, Dave, and thank you, Ben. Quality is good. Now, for the fourth presentation, we have using AI to assess compliance of pedestrian hybrid beacons in different roadway environments. Our presenter is Ron Knezevich. Ron is a traffic engineer and research currently working as a state safety engineering supervisor at the Georgia DOT. He uses data-driven practices and leverages a safe systems approach to reduce roadway fatalities in Georgia, primarily using highway safety improvement program funds. Ron is the GDOT Road Safety Audit Coordinator, Rural Active Transportation Land Manager, Safe Routes School Coordinator, and co-chair of the GDOT Safety Research Technical Advisory Group. Quinn is a current civil engineering student at Stantec University. He's also an intern this year for the GDOT Safety Engineering Program. Please help welcome Ron.
Good morning, everyone. I'm Ron. I'm the Safety Engineering Supervisor at GDOT. I'm here with one of my staff, Quinn. So we're talking about today how using AI to assess pedestrian compliance and study it with different signal timing and design for pedestrian hybrid beacons. So what we did here is at 15 pedestrian hybrid beacons, we modified signal timing and captured over 200,000 pedestrian crossings and detectively classified them. With those, we analyzed compliance. We found that longer delays at PHPs led to significantly lower delays or compliance for pedestrians. We found that at two-stage crossings, where you have to press that push button in the center refuge island, led to less compliance for pedestrians if vehicles were permitted to travel on the other side of that refuge island. We also found that longer staggers, or the Z crossings, we'll show a figure of this later, significantly led to less pedestrians crossing in both legs of the crosswalk. And then we also found, despite any modifications made to timing of these pedestrian hybrid beacons, and taking them out of coordination with downstream signals, we found that vehicle travel time was not affected along the corridor. So why are we assessing PHPs? Well, fatal crashes in Georgia for pedestrians have been increasing rather significantly. In the last 15 years, the number of pedestrian fatalities has more than doubled. Back in 2007, there was around 150 pedestrian fatalities, and that number is well over 300 today. So we need to change our approach to reducing these roadway fatalities, and that includes analyzing the existing countermeasures that we have out there. So pedestrian hybrid beacons, or PHPs, they are proven safety countermeasures from the Federal Highway Administration that we use those HSIP, or Highway Safety Improvement Program funds, to install. They're not just countermeasures for pedestrians, they have a traffic calming effect that is a proven countermeasure for all roadway users. But the research of both design and timing of these PHPs is fairly limited. Whatever we find on the design timing, we can't seem to find any studies backing up guidance related to it. So, with that, we posed a couple questions. So these topics in question are related to pedestrian delay, two-stage crossings, stagger length, or the Z crossings shown here, one on Ponce, DeLeon, and Atlanta, as well as coordination of PHPs and vehicular delay. So we leveraged AI and computer vision algorithm, as well as pro vehicle analytics to analyze the 50 PHPs on 4 corridors, capturing over 200,000 pedestrian crossings. That 200,000 number is already eliminating a little bit of data. Signals go out a little bit during the study. There's some faulty data that we have to remove. Still capturing over 200,000 data points. This data was collected in between August and October of 2023. It's a while to process. That's why we're here today with it finally processed and analyzed. And in that time period, we modified the signal timing and staging of those pedestrian hybrid beacons. That was done in cooperation with the SIGOS team. So data collection, this was conducted through a partnership with AECOM as well as company. Roadway users were both detected using AI algorithms. They were then classified as either pedestrians or bicyclists and vehicles. Tracking algorithms were also utilized to track the paths of those pedestrians as well. So a few different algorithms all in one. And since my IT department's here, I might as well say that this video log data is not what we receive as GDOT. We receive raw data. We do not retain video footage of this video log. So you can see a video here of kind of a sample of some of the data we're collecting. You'll see a pedestrian crossing, pedestrian path, as well as recognition as either pedestrian or a vehicle was classified, and the spatial location of the pedestrian vehicle is plotted as well, so we can see exactly where the pedestrian is walking within the crosswalk. So we collected data, these 15 locations here. We have a diversity in lane number, median presence, the speed, and the stagger distance, or that Z distance in the pedestrian refuge island. Into our first question of, did pedestrian delays affect a pedestrian's willingness to wait at these PHPs? So what we did is, for 6 weeks, we changed the timing of the pedestrian hybrid beacons. We changed it from 0 to 20 to 40 seconds of delay. Pedestrian hybrid beacons after coordination. We saw the delay before the yellow phase of that PHP was put into walk. We then tried to analyze compliance. Compliance is a pretty broad term, but what compliance means in this case is if they were walking on walk phase, so not in the yellow phase of the PHP. If you're not familiar with pedestrian hybrid beacons, they're off, they're solid black, then they flash yellow, turn solid yellow, turn red, and flash red. If the pedestrian was walking in the solid red or flashing red, they were considered compliant. We found that on 4-lane roads, changing the pedestrian delay significantly decreased compliance by 39%, going from 60% of pedestrians crossing in the walk phase to 21% of pedestrians crossing the walk phase at 40 seconds delay. That number of 40 seconds delay may seem like a high value, but actually if these PHPs are in coordination with downstream signals, it's not uncommon at all. That trend did not hold true, though, on a 6-lane road. 6-lane roads, people are a little more scared to, or a little less willing to dart into traffic on 55-mile-an-hour 6-lane roads. So we had about the same compliance of around 60% on the 6-lane roads. So again, that's why we have that diversity in lane number and speed to capture these different scenarios, because it's not all the same case. So I'm going to turn it over to Quinn now to discuss our next 3 questions. Our second one being, did 2-stage crossings affect pedestrians' willingness to wait?
Thank you, Ron. So did 2-stage crossings affect pedestrians' willingness to wait? So this is kind of how we broke it down. There were 3 sections of delay, 0, 20, and 40 seconds. And we had 15 locations. And we alternated between 1 or 2-stage crossing for each delay time. Excuse me. So what is 1-stage and 2-stage crossing? So 1-stage crossing, let's say you're a pedestrian, you hit that pedestrian push button. You were given a signal the whole way through PHG on both sides of the top. For 2-stage crossing, condition A, you are required to hit a second push button in the refuge island. However, both sides of traffic are stopped, and 2-stage condition B, where only one side is stopped at a time, and you are required to hit that second push button in the refuge island to stop the other side of traffic. So when comparing 1-stage crossing to 2-stage crossing condition A, there
there was similar trends seen in the drop of compliance. And it was a pretty dramatic drop of compliance when going from 0 to 40 seconds delay for the pedestrians. However, when doing one-stage crossing versus two-stage crossing in condition B, we have here on the left side of the screen again, condition B, only one side of traffic is stopped. One stage performed initially better in terms of compliance at 0-second delay. However, actually dropped a little below two-stage condition B when increasing the delay up to 40 seconds. So, for question number 3, did a longer stagger change pedestrian willingness to use both crosswalks? So a lot of these DOTs have what's called stagger, and the idea behind that is you're in the crosswalk, you go in the leg, you're in the refuge island, you physically have to turn your body to look onto the oncoming traffic. However, these staggers vary a lot in terms of their length. For our study, we looked at a couple 10-foot staggers and a couple 30-foot staggers. They range even more than that. You hit the smaller or larger. And when we took that stagger measurement, is as you can see in this third picture, we kind of took the middle of the crosswalk there, just kind of the average path of a pedestrian. So what would be considered compliant when a pedestrian is crossing a DOT with a stagger? What would be considered compliant is, here you can see in this picture, these are DCPIDs that the AI is picking up. They would have to pick up one or more of each of the IDs within each leg, and we could reasonably assume that they had used the refuge island to cross into the other leg. However, as you can see in that video that Ron showed a minute ago, a lot of people will continue straight instead of continuing straight. And they would be considered non-compliant for our analysis. And if someone, let's say they stepped on the street and then stepped right back off the street, or they crossed completely unrelated to PHP, we looked at one where it was the DCPIDs were on one side of the road going the wrong way. Like, what is that? And we looked at the video and someone had just walked on the wrong side of the road. It's like, okay, well, you're not considered. So when doing 4-lane roads, we looked at 4 locations on 2 corridors. There was a 25% decrease when looking at 2 locations with 10-foot stagger and 2 locations with a 30-foot stagger. However, for a 6-lane road, just like earlier, no trend was observed when increasing the amount of stagger. And all 4 of the locations we used for this question are all on Newford Highway, which is it's placed in Atlanta. There's a lot of cars, high speeds, and 3 lanes on each side. That extra lane makes a big difference when you're considering crossing outside of the stagger. So question number 4, was vehicular travel time affected on the corridor as DOT timing was adjusted? So we used ITSGA Clear Guide to pull all of our data, and here's the breakdown of the 6 weeks of the study. As a reminder, the delay is increasing, so it's 0 second for the first 2, 20 second delay for the second 2, and 40 second for the last 2. And we kind of pulled the route we made in ITSGA. We would include all the PHPs that we looked at and pull it from major road to major road. And this is an example of 1 mile corridor, and most of the routes were roughly 1 mile. So here was the median of the average travel time when pulling a typical weekday off of ITSGA. So we pulled every Thursday of the study. And here was that travel time in minutes. And here is a breakdown of the 6 weeks of the study to see if vehicular delay was impacted. If it was impacted, what we would expect to see here is a trend where travel time was initially higher, because that was, again, 0 second delay. And at the end of the study, it was down 40 second delay, so we would expect that to have decreased if vehicular travel time was impacted by pedestrian delay. And then we looked at the 6 weeks prior, the 6 weeks of the study, and the 6 weeks after the study to see
trend with how the study back in 2023 affected travel time along these corridors, and we did not see any trend. As you can see here, there's about a 5-second difference in the travel time from the three meetings there. So we could not find vehicular travel time increase along all of these corridors where we changed the timing out of system. However, as a reminder, the pedestrian compliance when increasing from 0 to 40-second delay had a pretty dramatic increase. It was, decrease. It was more than half in terms of the compliance. So I'm going to head back over on here.
Great. So to tie that all together, so 15 locations we assessed. We used AI to study various computer vision algorithms to detect and classify greater than 200,000 pedestrian crossings. We found that longer delays led to less compliance for pedestrians. We found that two-stage crossings, particularly that case B Roadway mentioned, where vehicular traffic is permitted, and you have to press the push button in the center island to stop them. That led to lower compliance. And we also found that longer staggers led to pedestrians less willing to walk in the legs of the crosswalk. And despite all those changes to VHPs, including taking them out of coordination with downstream signals, we could not find any change in travel time along those corridors. So thank you guys very much. We'd love to take any questions you have.
And now we will go for questions. We have about 10 minutes before we go on a quick break, so if anyone has a question. Yes?
I got a question for the guys from TDOT or GDOT. If you're finding that compliance was decreasing, you having with the hybrid pedestrian crossings, were you having a harder time selling that back to GDOT leadership of being an effective countermeasure?
Despite the crossings not having full compliance, we know they reduce crashes. We see the crash reduction. Really what we're looking at here is how do we maximize that crash reduction. So, we can change timing to try to make them less compliant. So the best case scenario is one-stage crossings with 0-second delay. We see around 70% compliance. Again, they're proven to reduce 55% of pedestrian crashes. That's not the full solution to reducing 100%.
So even though there's decreased pedestrian compliance, it lowered.
Still lower crashes on these various corridors, in particular Beaufort Highway. We know that one has a really strong crash reduction.
My question is about the pedestrian study as well. I love the clarity of the results, pretty amazing. I'm just curious if you had near-miss data and if you looked at the near-miss data through the lens of these 4 variables as well.
We did look at near-miss data and could not find trends with near-miss data. That's because we don't know exactly how near misses correlate to crashes. So we looked at compliance at this point. I'm a big proponent of the use of near-miss data, so don't let that shy away from it. But for granular studies like changing the timing of signals compliance was I think a better metric that showed trends. We just didn't find anything with near misses, including vehicular near miss data as well for variance.
If compliance has a strong relationship with the crashes, or there might be other reasons that is more affecting more crashes than compliance as well. I mean, each compliance is one of the strong factors. E-compliance is one factor that affects implementations.
This study analyzed the design of the PHPs and the timing of the PHPs. So those two variables were considered with the compliance analytics. This was not a before-after study with crash data.
So I do agree proactive safety measures are a lot more effective than historically reactive measures that are used to analyze crash data. You had a top view of the scene, so I'm guessing there's a lot of post-processing that happens to the data that comes in real time to visualize it and then calculate those measures, either time to collision, post-encroachment time, etc. So maybe you can elaborate a little bit more on the processing time and how long it may take to actually respond or prevent a potential conflict scenario.
Yeah, so right now, the AI system, the AI analytics, it can send information out to the field if it sees a potential conflict for warning. And now you're getting into sort of a connected vehicle and a connected people type of scenario. So right now, some of the deployments are energizing signs to warn the driver that a pedestrian may be there, those kind of things. So that would be real-time interaction when we're trying to be more proactive. It's basically looking at those data sets that you're collecting. So even if you collect 2 weeks of data, you can see where potential problems may exist within that 2-week window, and then you can start reviewing what are the solutions that may either contribute to that problem or a resolution to that issue. When I was at DOT looking at accident data, it basically was a 3-year rolling window of accident information that you look at. And a lot of times that is far past the idea of being proactive. So very reactive. So this just gives the traffic engineer a quicker window to look at potential problems. Even on new deployments, you can have that. So if you put in a new deployment, sometimes you don't understand what the behavior of either the vehicles or the pedestrians are going to be, but you can then measure that and see that and maybe make adjustments within your project window as well.
Thank you, Dave. And if we do not have any more questions, I could, Rocky, yes.
I have a question to So, as we are talking about the TSMO deployment planning process, so there was on part like performance measurements and operations. So at that stage, like you are showing some performance metrics and some results. So I'm just curious to know, like for your case, like how did you identify the metrics that are going to represent how you're going or how you're trying to achieve. So my question is like, how do you define or identify those particular metrics?
Yeah, that's a good question. I think so speaking of performance metrics, when you talk more about asset management, it's looking at a lot of how you're performing, age, condition, the technologies, the technology outdated. So it may not be necessarily purpose, but it's more about the needs of today, is meeting the emerging needs that we have as a department. So through more advanced metrics and trying to get those fields attached to those attributes, then you can really start to determine, okay, for instance, cameras, can we not see as well with cameras? High resolution type cameras, age of equipment, hey, it's reaching the end of its useful life, probably starting a problem. So it's variable types of things depending on the type of equipment that we're tracking.
Thank you.
Thank you. Yes.
This is directed and Tennessee DOT representatives in front of the room today. A lot of crash data, for instance, and other collected information, there's a pretty strong, policy manner of how you store that data. And for the public sector, a lot of data is requestable public information, so if the public asks for it, you have to provide to them, which is sometimes the reason that public sector doesn't store, for instance, live video from traffic signals and traffic cameras. How, if at all, have you guys seen that near-miss information that you're putting out in locations? How are you seeing that stored? And specifically, when you talk about the location where you get near-miss and the video from that near-miss, how is that being stored? How is it being relayed to your public sector clients? And what are you seeing them do on their side on storing that and dispersing that if requested by constituents?
So this is an interesting topic because when I was at the city for about 10 years, we were doing exactly that. And so how do you protect the city, especially with the requests from the public? So what we've seen is a couple of things. The migration to the cloud, basically it takes it out of the public domain of the city or state, and it puts it in the private domain. So the request for all that information does not comply. It complies to what is there for the public person. So that is one of the trends that we see. So a lot of these video clips that are taken are stored in the cloud. They're not stored locally on the agency's computer or anything like that. The other solution which is kind of a roundabout way to do it when I was at the city, is that we would store and record over certain things like video and those kind of things, and we would basically record a week's worth and then write over. But then we put it in policy within the city to say if you get a request for information, it has to then go and get reviewed by legal teams and all those kind of things. By the time the request came to my desk, it was too late. I don't have that data anymore. So you build in a delay of the paperwork process to protect you from the city of saying, I have to turn it over right away, right? So that was just a formal process that utilizes the inefficiency of government, to say it nicely, to basically delay it so that I don't have to basically keep all the data, but I do get it if I need it, and within a week I can look at it myself, and if the police or fire need something, I can give it to them that week. That creates a different problem because then I have recorded a video of that incident, and if it goes to the fire and the police, then it is on record. So you have to deal with this.
Thank you, Dave. And then one last question in one word, no thinking. What is the future of ITS?
Collaboration, integration, exciting,
interoperability,
Incorporating safety in that, yes.
community.
Security.
He's still my there.
It's a good topic.
Security.
Thank you, everyone. And with that, we conclude session number 3. We're going to go on a quick 10-minute break because I want to finish short of time. And the presenters for the next session, please come to the stage. Thank you.